In this segment, we're going to talk about forced oscillations and resonance. And we're going to start by talking about something called damping. And damping is essentially when we have outside forces, outside resistive forces acting on our oscillating system. We know that a lot of the stuff we talk about is theoretical, and in these frictionless environments, but in reality there are things like friction and air resistance that have an impact on the motion of the object and cause things that are moving to eventually stop. The same is true in oscillating systems. If we're talking about true simple harmonic motion, in an ideal situation, the amplitude of the oscillation would remain constant. That means that it would go to the same maximum displacement every single time in every single oscillation. But we know that if we're to pull a pendulum back and release it, or get a spring oscillating up and down and let it go, eventually those two systems are going to come to rest because of the forces of friction and air resistance. And we're going to see that amplitude decrease gradually over time. This is what we call dampened oscillations, where you have those other outside factors affecting the motion, affecting the amplitude, and it causes them to eventually stop. And in these situations, just like when we're talking about friction on something moving across the floor, moving in translational motion, the forces are always opposite the direction of motion. They're doing negative work on the object, taking energy out of the system. And so, as we said, we talk in ideal situations a lot of times, but because it's impossible to get rid of all friction, in reality all oscillations are to some extent damped. And so what we do is we classify them based on the degree of damping. We can have something that's lightly damped, and this is something your normal pendulum oscillating back and forth that's very slowly, very gradually decreasing in amplitude. It's going to make a lot of oscillations before it eventually comes to a complete stop. Or we have heavily damped systems, and this is where there is an enormous amount of resistive force and there's a very, very quick decrease in amplitude, and the system may only oscillate once or twice before coming to a complete stop. And a lot of times our heavily damped systems are intentionally heavily damped, as we'll see. So our graph on the left is a lightly damped system, and you can see in this diagram that there's 1, 2, 3, 4, 5, 6 oscillations just on the graph, and then it's continuing on, so it hasn't even stopped yet. But you can see how there's a very, very gradual decrease in the amplitude of oscillation. Then the one on the right, we have one complete cycle from this point to this point, and there's a very drastic decrease in the amplitude, and the actual system only gets through 1 1/4 complete cycles before it actually comes to 0. Then kind of our main extreme, our far side of the extreme of this is what we call critical damping. And this is where the system that's oscillating comes to rest when it reaches equilibrium position. So it doesn't even get through a full cycle. It begins to oscillate, passes to that equilibrium position, and by the time it gets back, it stops. And this is a result of very, very strong resistive forces to get it so that it stops that first time it reaches the equilibrium position. And so it's going to look like this. You can see the displacement, and as the displacement reaches 0, it stops. It doesn't go back away from and eventually it's going to go down here. So it's going to reach equilibrium. And it doesn't ever leave that again. Now, some examples of damping that we see kind of in everyday life. Tennis players, that little plastic thing that's at the bottom of the strings is a damper to help control the oscillations. When we're playing baseball, the reason that there is that sweet spot is that when you hit the ball in the sweet spot, it minimizes the transfer of energy into the that gets wasted in the bat, and it minimizes the oscillations in the bat. And that's why if you hit it closer into the handle or further out, the main reason it hurts your hands is because it gets the baseball bat actually oscillating, and so that's what hurts. Suspension systems in cars are a great example of damping. The shocks and the struts, the idea is that as they go over bumps and things like that, the car starts to oscillate, but the dampening system in the suspension stops it from just oscillating back and forth wildly. If you've ever been in a car that has really old shocks or really old struts that have lost some of that ability to dampen, you'll know the difference because you'll hit a bump and you'll go up and down, up and down. It'll feel like you're on a roller coaster ride. They also build buildings in earthquake-prone areas with we call damping systems to help protect them against earthquakes. And then also in pianos and guitars, you have damping systems that control the oscillations of those strings. So then the kind of the opposite of that is we call forced oscillations. And this is what this is when we actually force something to continue oscillating. At this point, we've just been talking about objects oscillating. You set them to oscillating, and they oscillate at their natural frequency. And the natural frequency is just the frequency at which that system would naturally oscillate. So if you set a pendulum in motion, we know we can calculate the theoretical period, and it's related to the length of the string. Right, length of string and the gravitational constant, lowercase g. With a spring, the natural frequency is related to the spring constant and the mass that's hanging from it. So there are things that affect these natural frequencies, and pretty much every object has a natural frequency. If you have a wine glass and you rub your finger around the tip of it and you get it so that it makes that humming sound, that's the natural frequency of that glass. When we're talking about forced oscillations, though, forced oscillations is when we're causing a system to oscillate at something other than its natural frequency. And an easy example to kind of picture this is a kid on a swing. And say you got your little brother, little sister, or big brother, big sister, I guess, depending on your specific situation. If they're on the swing and you push them, again, that's going to be dampened harmonic motion. So eventually they're going to slow down and stop if you don't continue to push them. If you time it right and you push the swing as it's coming up to its maximum amplitude and as it's starting to go back away, you're going to be adding energy into the system at a very very efficient rate, and so the swing's going to go higher and higher and higher. If you push them when they're still coming back at you, it's out of phase, and so your frequency is going to be different than the frequency of the swing, and you're going to be trying to force the swing to oscillate at a different frequency. And in that case, the energy is not being transferred particularly efficiently, and so you actually lose a lot of energy. So the closer to the natural frequency of that particular object that the driver is, so you in this case, the closer to the natural frequency of the swing that you're pushing the swing, the more efficient the energy transfer is going to be. So if you're in sync with the swing, you're going to get a lot of energy transferred in, and the swing's going to go really high. If you're out of sync with the swing, then it's awkward, and it's not a very fun ride for the person on the swing. And when we're talking about those, how close they are in sync, we're talking about how their phases compare. And so if you're synced up exactly with the frequency of the swing, that's called in phase. And so if you and the swing if you pushing and the swing's oscillations have the same frequency, then the two of you are in phase. If they're not the same frequency, they're what we call out of phase, and then we start talking about by how much. And the variations in the amplitude, and again, what we're talking about here really is how much energy is transmitted into the system versus how much is lost. Because if we have more energy going in, the amplitude increases. If we have more energy going out, the amplitude is going to decrease. The things that impact that are the frequency of the driving force and the natural frequency of the system. The amplitude of the driving force, which in our case would be how hard are you pushing. The harder you're pushing, the more the increase is going to be. The phase difference between the driving force and the natural frequency, which is what we just talked about. If you're in phase, there's going to be a much higher increase in amplitude than if you're out of phase. And then the amount of damping. So these 5 things are really talking about the relationship between the frequencies and the relationship between the forces involved. Is the driver and the object in frequency or in phase or out of phase? And what's the comparison between the driving force and the resistive force? If the frictional force is greater than the force that you're applying to the system, then the object's going to slow down, or the amplitude is going to decrease rather. The frequency will stay the same. If the driving force is greater than the damping force, then the amplitude is going to increase. And this is what we just mentioned. If they're in phase, it's going to get the maximum kinetic energy from the driver. So when they're in phase and there's a lot of energy in the driver, you're going to see that amplitude increase. What we mentioned earlier also is the frequency between the driver and the natural frequency sync up. You're going to find that that's going to increase the efficiency of the energy being put into the system, and the amplitude is going to increase more quickly. But again, that's going to be countered by the damping effect, and so the more friction there is, the more air resistance there is, the less that amplitude is going to increase. And here we just, you can see that if the frequency of the driver, which we'll call F, is equal to the natural frequency, which we'll call F sub 0, you get a very steep peak where we're increasing the amplitude significantly. And then as the amount of damping changes, the amount of increase in the amplitude is also going to change. And so this steep peak here is very light damping, and so if there's very little friction acting against the driving force, there's going to be a much larger increase in the amplitude. If there's a little bit of damping, kind of a medium amount, you're still going to get an increase if those two frequencies are in phase, but it's not going to be nearly as much. And then if there's a significant, very heavy amount of damping, then the increase in the amplitude is going to be much, much smaller. If the force of the damping and the force of the driver are the same, then you're going to see no change in the amplitude because those two forces are going to cancel each other out. And then along with this, we have this idea of resonance, and this is basically what happens at this point here when our frequency, let's pick a new color. When our driving frequency, go away, when our driving frequency is equal to our natural frequency, and there's that very, very efficient addition of energy, and we see a significant increase in the amplitude. That's what we call resonance. And this, again, when you run your finger around a wine glass, that's resonance. When you blow air across the top of a bottle and you hear that that tone that gets created, that's resonance. If you've ever seen the video of the Tacoma Narrows Bridge, basically the wind is blowing across, causing the bridge to oscillate at its natural frequency. The frequency in the wind is the same as that natural frequency. It adds energy to the system, and the bridge starts oscillating so much that it tears itself apart. And again, the idea here is that when those two frequencies are the same, the addition of energy into the system is incredibly efficient, and you get the maximum input of energy, and so the amplitude will continue to increase. With wine glasses or with glasses, if you've ever seen videos of somebody shattering a wine glass with their voice, they did a Mythbusters on it. There have been some other shows that they've done it. But a person can actually shatter a wine glass with their voice if they can sing the exact note that's the natural frequency of that particular glass, because it's adding energy to the system until eventually the wine glass is oscillating so much that it just tears itself apart. And that is that for this segment. So let's stop.